Let me continue to study on the treating behavior of a general section, general cross section, so non-circular shaft. Let's look at the kinematics. Let's consider arbitrarily shaped cross section. Looks like this. And let's define a coordinate system on the section. And this section will rotate about the origin of this coordinate system. And direction of rotation is this. This is a twisting rotation. So, what I like to find is that displacement. Displacement U. So, U X, U V, U Y, U W. So, when a bar with a general cross section looks like this, let's find the displacement of cross section G. Here, let's consider some point xy here, material point xy. Okay. Okay, so, and this will move to here, this new point with the rotation pi. And pi is a twisting angle. Pi is a twisting angle. And angle. Actually, pi is a function of x in general. How can I find this new point? We need some simple geometry. Stop. Let's say this is the y-axis here, and this is the point, x and y material point. This point go in this way. Pi. What's the length of this movement? Pi r, right? Let's think this is r. R equal square root y square g square. R is the distance from the origin. Right? And let's draw triangle. Looks like this. Triangle. And here, let's consider two triangles. First triangle is this one. Okay. This is right. Have a right angle here. And second triangle is this one. It has a right angle here. actually both triangles are similar, right? So they are sharing this end, right? This. So this angle and this angle should be same, right? Let's say this angle is just theta. Theta. Okay? So let's consider only this part here. So over there we can draw triangle again. So here theta, from here to here, pi r, okay, and now I'm considering this. So originally this point moved to this point. So what's this? This is a y displacement. This is uy. And this is your x displacement, ux. Right? Now from this triangle, we can calculate the displacement in y and g direction. So uy, sorry, this should be ug. uy equal minus r pi sine theta, right? And ug equal r pi cosine theta. This is just a result of simple geometry, triangular geometry, right? And here we need to think about sine and cosine theta. Okay? This is theta here. Okay? And let's consider this triangle. So, what's this? From here to here is a y. And from here to here, g. Then we can calculate the sine theta and cosine theta with x and g, y and g. So sine theta equal g r, cosine theta equal y r. Right? So I drew a lot of line. So finally, uy become, let's put this result into here, okay, minus pi g. ug become pi y. This is a rotation of the section. So and ux. Now we need to think about displacement in x direction. So during this twisting, okay, you understand the displacement will be appear in y direction and g direction. Then how about displacement in x direction? X direction means displacement in out of plane direction. Is it possible? No? It's possible, actually. If you twist some member, we can have a displacement in length direction. And this is a function of x, and y, and g. Okay? We are saying this is a warping displacement. Actually, if we twist the circular member, okay, then there is no warping. But if you twist non-circular shaft, there will be a warping. So when we consider the twisting, it's very important to consider warping effect. So we need to remember there are going to be displacement in this out of plane direction. We are saying this is warping. So, for example, this is a I section beam. Looks like that, right? If we twist this, what happens? This part go back, this part go forward. This kind of warping will happen. So if you view this from the top, okay, this top plate displays like this, okay, and bottom part displays like this, okay. This is maybe we are saying this is warping. So when beam is subjected to twisting, out of displacement happen, we are saying this out of displacement is warping. So in general Euler beam theory and Timoshenko beam theory, this warping is not considered, right? So Timoshenko and Euler beam theory cannot properly approximate the twisting behavior. Both theory is only for bending. It's not about twisting. Okay? Okay, so now we know the strain. We assume the strain. No. We know the displacement fields like this during the torsion, right? We can calculate the strain, right? From the displacement strain relation. Strain. So strain xx dx dux, right? It will give dx df g y x, right? How about strain yy? And strain gg is 0, right? uy is not a function of y. ug is not a function of y. So both, so strain, normal strain in y and g direction is 0, right? And how about the engineering shear strain, gamma yg equal uy plus ug, So let's take the derivative about g over there. So minus pi plus pi rotation angle. So it becomes 0. And gamma xg become g ux x ug equal f g plus y pi. Then gamma xy equal ux uy equal f y g plus minus g pi. So we have only 3 strain, non-zero strain in extraction, normal strain, XX, and 2 transposition strain. So this is just a solid mechanics problem, right? Unknown is this function f and g, right? If we find f and g, we can calculate everything. Okay, now let's simplify the problem when each cross section is subjected to the same moment. It means uniform torsion. Uniform torsion case. Torsion case. Uniform torsion case. So when the cross section of the beam subjected to the same moment, uniform moment, okay, and or we can say this is a pre-warping case. So in this case, Fx is constant. Also, we assumed ux equal fx and g, y, and g. So warping displacement is a function of x, y, and g, right? And this function made by the multiplication of function about x, function about y, and g, right? So this part is only function of x. So if the uniform torsion case, this fx becomes just constant. So, and dx, d pi. Twisting angle also constant, same twisting angle. I mean the constant rate of twisting angle. So rate of twisting is constant. Constant. Let's say this is K. And in this case, Ux become simpler 3 constant G, Y, and G, right? Become simpler. And let's modify this function a little bit. K, C, K, G, Y, G. Okay? Using the constant K, and it become K and K pi, which are the other, Y, G. We are saying this is a warping function. Warping function. And Uy become minus K xg, Ug become K xy, because from this equation pi become kx, right? Instead of phi, we can put kx, right? This is pi. So by introducing warping function and some constant k, equation is changed for a little bit. Then let's calculate the strain again in this special case. Let's use that free displacement field and put that field into here. Then strain xx become f is a constant, so it becomes 0, right? xx 0 and strain yy gg gamma yg was already 0, and strain xg become k y plus g, and strain xy k minus g plus pi y. So we have only 2 strain remain. Now we need to consider only 2 strain. So you remember displacement method? We are using displacement method. Typical displacement method. First, we found the displacement field for the twisting case, and then we calculate the strain. Then what's the next step? We need to find stress, right? Let's calculate stress. How? We need to apply material law. So if you apply material law, we can identify the stress xx, yy, gg, and stress yg is 0, right? Because the strain of the corresponding stress are 0. So only 2 non-zero stress exists, xg, by multiplying the shear modulus g, k y plus g, and stress xy gk minus g plus k. So now we calculate the stress. You remember what's the next step? So, what's next step? So we know stress, equilibrium equation, right? So now we need to use a local equilibrium equation. Local equilibrium equation. So with only those two stress components, we need to consider only one local equilibrium equation. So actually we have three local equilibrium equations, right? But among them, this is the first one. Sorry, this is one of them, and other two. Y x is 0, x g x is 0. So two local equilibrium equation is already satisfied. So only one, we need to consider only one local equilibrium equation. Okay? And in this equation, let's yield this result. Then from this equation, we can have gk pi plus g pi equal 0. So we can find out this result. The form of this equation looks like something, right? Which you are very familiar with. So that is a Laplace equation. Y equals 0. Okay, same thing. In the cross-sectional domain, this is Laplace equation. Right? Definition of this: partial y, partial also right? This is Laplace equation. We can see the Laplace equation in fluid mechanics, continuity equation, right? For incompressible fluid, same thing. So this equation, this Laplace equation mean local equilibrium equation on the cross section, in the cross section, right? So when we solve solid mechanics problem, there has been two equilibrium equations. One is a local equilibrium equation in the body. What's the other one? Another one is the equilibrium on the surface, right? Now let's consider equilibrium on the surface. So this is cross section, y-axis, g-axis. Let's consider surface defined by its normal vector n. Okay, and stress n equal 0 on this is a surface is this partial omega, right? This was equilibrium on surface. Okay, and let's divide this vector n in two components, m and n. So n become 0, m, n, right? 0, m, n. N is the direction vector. So now, in this case, we are only considering 2D domain. So in x direction, the component of the vector should be 0. And let's consider this equation. We have only stress component x, y, and xg. yx, stress, gx, and others are 0. And let's put 0, m, n. It become, B should be 0, 0, 0, right? So this equilibrium equation on the boundary gives us result in the m stress xy plus n stress xg equal 0, right? If you multiply and apply the first row and this vector, and we can have that equation. And this row and this row result in 0. So we need to consider only that equation, right? Okay. Then this equation means mgk minus g plus y ngk y plus g pi equal 0. finally, M plus N equal mg minus ny. This is another equilibrium result of from the equilibrium equation. And then left part is same to the n dot this, right? Same. On surface. So finally, we can find the carbon equation. Carbon equation. Carbon equation is that N equal mz minus ny. Mz minus ny on this is our carbon equation for the twisting problem. So if we solve this problem, this carbon equation, we can find out what? Warping function. So once we know warping function, we can calculate stress, strain, and displacement, right? So warping function is one of displacement. This is very well-known equation. Its name, Saint Bernard equation. Saint Bernard equation. This is very well-known, famous equation, Saint Bernard equation. So equation looks like quite complicated. So for very simple cross-section, we can directly solve the equation, but for general cross-section, it's almost, we need to use a numerical method. Now let me talk about how to calculate the M and N. M and N is determine the direction of vector normal to the surface, right? So let's say this is a domain and let's define the coordinate S. S is a coordinate through the boundary. Okay? S is a new coordinate. Okay? And let's consider here normal vector N. This is normal vector, this is tangential vector T. This is tangential normal. So, how can I calculate tangential vector? How can I calculate tangential vector? So here the y is a function of s. Okay, g is a function of s. So here point is a y and g. When the y is a function of s, g is a function of s, then we can easily calculate the tangential vector 0 sy s g. Right? How about n? Normal vector n can be calculated from the t. If I take the dot product t and n, result should be -1. You remember? So n becomes 0 s g minus s y. So this become m, this become n. So we can calculate the m and n in this way. So then the second equilibrium equation become changed a little bit. G plus y s g minus y plus g y s y equal 0. Okay, so let's finish today's lecture here and then. Any question?